This is the first of a series of lectures about analysis of variance. Of course, all the cool kids call it ANOVA. This is all about comparing the means of more than two groups, which usually arises in situations prompted by experiments and the collection of experimental data. So first, let's talk about experiments a little bit. Good experiments these days are all designed experiments. And so let's talk about some basic elements of experiment design. In experiments, we want to manipulate causative variables in controlled conditions. That is, we don't want things changing that might influence the outcome of the experiment. The reason is to establish cause and effect relationships. So X is the thing we manipulate, and Y is the thing we measure to see if the manipulation did any good. Design has several goals. The first is to avoid confounding, either of characteristics in treatments or among treatments. For instance, if I had an experiment where many of my subjects were women, but only the women were given a certain treatment, we'll call it treatment A, then any effect may be attributed either to the treatment or simply to the fact that the subjects were women. That's confounding. Another goal in experiment design is to isolate the effects of known variation. Oh my gosh, if I have subjects that are either men or women, I'd like to see how much variation is imposed by the differences of men and women. And finally, I'd like to reduce the effects of unknown variation, because subjects do differ. And so I'd like to have those differences spread out across all my treatments and not bunched up into one of them. So some design techniques we use to get there. First, we use subjects from a homogeneous population, so reduce subject variation. Hold outside variables constant, which could be time of day, temperature, humidity, etc. We can group or block subjects with common characteristics, e.g. sex. That is, one group is women, one group is men, and then each group gets all the treatments. And then finally, we can randomize subjects among the treatment groups. Here's a nice example. We're doing a horticultural experiment where we're testing the effects of different fertilizers. So we have 3 fertilizers and a no fertilizer treatment. We have an experimental plot that has 24 subjects in it, but we see that there's a varying microclimates. So we have microclimates here. And so we block according to the microclimate, and then within each block, we randomly assign the treatments. So random within block. And so we've done both things, blocked and randomized. This is an example of what I call the ANOVA mantra. Block for known variation, randomized for unknown variation. A certain type of experiment is called a clinical trial. And a clinical trial is no more than a randomized medical experiment with human subjects. These have requirements, techniques, and jargon all their own. Probably the most important thing about a clinical trial is the idea of informed consent. So this is required in all civilized countries. And Basically, is the idea that no one should have a treatment applied to them unless they know its possible effects, and also that they may cease participating in the experiment at any time. Clinical trials always have a control group, what we would call a null treatment. And most modern clinical experiments use some sort of blinding. Simple blinding means that the subjects are unaware of treatments. Double blinding means clinicians, that is, the people applying the treatments, are also unaware. And to make this easy, we very often use a placebo, which is the null treatment. There are actually some surgical experiments that have a surgical placebo. They make a little incision while you've been anesthetized, and then they just sew you back up. Nowadays, clinical trials are categorized in 4 phases. 1, 2, 3, and 4 are in the labs. And phase 4 is out in the general public. Here's a quick summary, so you don't feel completely at the sea on these. Phase 1 is what we would call safety testing. We don't want to kill anybody with our medication. Phase 2 is effectiveness. Phase 3 is comparisons with other treatments and also testing for side effects. But of course, some side effects don't show up in the short term, and so that happens in phase 4, and so this is long term. But in phase 4, the medication has actually been approved and released to the public. So in phase 4, you're the subject. Enough about experiments. Now, how do we analyze these guys? Well, we actually have to use kind of a trick. ANOVA is a trick. ANOVA is a trick to avoid this problem, experiment-wise error. When we compare the mean effects of several different treatments, we ask if the effects are same or different. The null and research hypothesis are, well, the null, all the same, or the research hypothesis, at least one is different. Up to now, all we know how to do is a 2-sample test, like the t-test. But if we have k treatments, we have k choose 2 pairwise comparisons. For instance, if k equals 4, then 4 choose 2 is 6 comparisons. So the number of comparisons goes up very rapidly in relationship to the number of different groups we're comparing. Now, each has a type 1 error, alpha. The probability of not rejecting the null is 1 minus alpha, so that's for one comparison. The probability of not rejecting H naught, the null, means you have to not reject all the comparisons. So that probability is 1 minus alpha to the m power. And then the experiment-wise type 1 error is just the complement of that, so 1 minus that guy that we just calculated. Let's look at an example. When I have 5 treatment groups and alpha is 5%, well, 5 choose 2 is 10, so there's 10 different comparisons. I'll plug in the alpha and the 10, and I'll get an experiment-wise alpha of 40%. Ouch. That's way too high to be practical. Now, the solution to all this happened about the time of the of the First World War. And this was an idea that basically was compiled and refined by Ronald Fisher. And so he zeroed in on the idea of variance, our old friend variance, and he developed analysis of variance as the way to compare several means. The key to this is something called the sum of squares identity. So the sum of squares identities, pretty neat. You can figure it out with simple algebra. He says take the total sum of squares. So find the deviation from the grand mean of all observations. So that Yij is one observation. We'll calculate the squared deviation of all the observations from the grand mean, add them all up. That'll give the total sum of squares. Now, a little algebra says that this total sum of squares can actually be broken into two parts. The sum of squares for treatments and the sum of squares for error. So, treatments. Okay, so treatments says, oh, let's compare the grand mean to the group means. Square those deviations, multiply them by their number of observations, add those up, and the variation within each group. So individual observation minus group mean, square those, add them up again over all groups. All right. Fisher was kind of modest about that. He said the analysis of variance is not a mathematical theorem, but rather a convenient way of arranging the arithmetic. Wow, too modest. This is the key to most modern statistics. We'll see this a lot. Now, how is this going to help us? Well, let's look what the sum of squares looks like under the null and alternate hypotheses. So here's the null hypothesis, okay? And so what we're going to see is sum of squares for treatment is small. Compared to the sum of squares for error. Under the research hypothesis, now the sum of squares for treatment is large compared to the sum of squares for error. Fisher seized on this and he says, gosh, when this ratio is large, the means are going to be different. So we can actually compare the means, not by comparing means at all, but by comparing variation. Let's look at an example and see how these numbers might work out. So here's an experiment where we have three treatments, knee, waist, and eye. We'll talk about what that experiment is in a future lecture. And here's some summary statistics, group sizes, group means, and group variations. And then we'll look at some quick formulas for figuring out our various sums of squares. This one's probably the most important. We can take the individual group variances, multiply them by their degrees of freedom, add them up, and get the sum of squares for error. Okay, so let's do this. Sum of squares for error. Each group has 7 degrees of freedom, and so 7 times each of the variances will give us a variation of 303.8. Sum of squares for treatments, we'll look at those deviations from the grand mean and square them, multiply by group sizes, and add all those up. Okay. And then the total sum of squares. The total sum of squares simply says take the overall variance, 2966, Multiply by 23, degrees of freedom overall. Ooh, 8 carrier 1, 9 carrier 1, 8 carrier 1, 7, 8. And 2, 3, 9. Stop. Finally, total sum of squares. Multiply degrees of freedom overall for the experiment times the overall variation, 68.18, which is just the sum of these two. So, we can decompose the sum of squares. In our next lecture, we'll talk about what we do with those sums of squares to do the test.